Alright, hello everyone, welcome back. I'm your friend InsXO. Today, I'm going to do some little changes about my life. Normally I would try to do the learning at the morning because only in that time I would have some spare time to do whatever I want to do. But recently I start to find that I don't have that spare time in the morning anymore because there's a guy in my office. He always, let's say, came to this office at the 7 a.m. and normally what he do is play mobile games. And to be honest, I do not understand why he could play his mobile game at home, why he want to come to the office and play that kind of stuff for a whole hour. That makes sense to me. And yeah, since if that's the case, since I could not control others' life, people could do whatever they want to do. It's their freedom. I cannot control them, or I shouldn't control them. So I think the best way to solve this problem is to actually change myself. I could stay up late. I could stay late or later at the night, then sleep longer at the morning so that I could fully use my time for a little bit. And for me, the most easy way to learn is to read something. I was always the kind of guy who tried to speak something while I was learning, and I think this is very efficient for me. And when I speak, I do not have to spend a lot of energy on what I am doing. I would feel like it's a very fluent thing to do. And here we go. We're gonna try to learn an algorithm. And for this book is, let's say, what do they call? Interview Problems, Dynamic Programming with Python. And I have read the first two interview problems, then I'm going to get into the three. And for the third one, the title for it is Change Making, Giving a money amount and the list of coin denominations. What's the meaning of denominations?
Denominations.
Alright. So giving a money amount and the list of coin denominations provide the combination of coins adding up to that amount that uses the fewest coins. You know what? For me, whenever I heard this kind of problem, I have no way to solve it. I have no ideas of how can I solve it because it's too open to me. I couldn't think a straight way to solve it. At least for me, I don't know how to do that. So that's why I want to learn this book. That's why I want to learn something from this book because I need it and because that's what I do not know before. Alright, let's get started. The example 1. Pay amount 9 using coin denominations 1 to 5. The combination having the fewest coins is 5 to 2. A suboptimal combination is 5, 1, 1, 1, 1. It adds up to 9, but it's using 5 coins instead of 3. Thus, it cannot be the solution. The solution for this problem should be the optimal one. So for this case, I'll be 1 to 5. But you know what? Even for a real person, he couldn't get the answer immediately. He had to do a lot of try and fails to get the right answer. Yeah, that's why I sometimes feel very hard to solve this problem because if I do not know how to do it with a human way, then I probably couldn't be able to do it with a programming language, right? Because we don't know how. The example 2, pay amount 12 using coin denominations 1, 6, 10. The combination having the fewest coins is 6, 6. A suboptimal combination is 10, 1, 1. So at the first we need to clarification. Sorry, what's the meaning of clarification questions?
Clarification questions.
Clarification questions. What result should be returned for total amount 0? The answer is the empty list. Is it possible that the amount cannot be paid with the given coins? Yes, for example, the 5 cannot be paid with coins 2 and 4. In such a situation, return none. Alright, by doing the two question and answer activity, now we know more about the question itself. But that doesn't really help us to solve this problem. We need to find a way to do that. And here's the solution 1. Dynamic programming, top-down. We can formulate a top-down dynamic programming solution if we model the problem as a recurrence. For any non-zero amount that has to be paid optimally using the given coins, we know that at least one of the coins has to be used. The problem is that we do not know which one is the one. If we knew, we could use that as a starting point to reach a sub-problem. We could subtract its value from the amount, then solve an instance of the problem for the remaining smaller amounts. We could continue in this way until the remaining amount becomes 0. Yeah, this is probably I won't say it's a good way, but it's probably a way that everyone could think of.
Brute force algorithm.
Some people would call that kind of method a brute force algorithm, and I agree with that. This is the one that we could easily think of or come up with or in our mind. However, we do not know which coin to choose first optimally. In this situation, we had no other choice but try all possible options in brute force style. I was kind of love the brute force style because normally that's the only way that I could think of when I want to try to solve a problem. For each coin, we subtract its value from the amounts, then solve by recurrence the subproblem. This leads to a candidate solution for each choice of the first coin. Once we are done, we compare the candidate solutions and choose the one using the fewest coins. Yeah, this is definitely belongs to the brute force style of algorithms. And here's an example of how we would form the optimal change for amount 9 using coins 1 to 5. We represent each amount as a node in a tree. Whenever we subtract a coin value from that amount, we add an edge to a new node with a smaller value. Please mind that the actual solution does not use trees, at least not explicitly. They are shown here only for clarity. Yeah, of course. So at the beginning, we got the number line, which is the total amount that we have. Then we got a few coins, the 1, 2, and 5. This is all possible choices for the first coin. Then after we taking the first coin out, then we will get the 8, the 7, and the 4. And we could easily find the optimal solutions for each of them. For example, the 4 would be just 2 and 2. The 7 would be 5 and 2. The 8 would be 5 to 1. Well, why we know that? As I think, the only number that's smaller than 4 but still the comparable bigger value would be 2. And for this one, what kind of number that is smaller than 7, while also the biggest one in this list of coins? Well, that will be just 5. So that's why we choose a 5 as the first one in this list. Something like that. This diagram shows that for value 9, we have 3 options for choosing the first coin. We choose coin 1. We now have to solve the subproblem for value 9 minus 1, which is 8. Suppose its optimal result is 5 to 1. Then we add coin 1 to create the candidate solution. 5, 2, 1, 1 for 9. If we choose the coin 2, we now have to solve the subproblem for value 9 minus 2, which is 7. Suppose the optimal result is 5, 2. We add to it coin 2 to create the candidate solution 5, 2, 2 for the 9. If we choose the coin 5, we now have to solve the subproblem for value 9 minus 5, which is 4. The optimal result is 2 and 2. We add to it coin 5 to create the candidate solution 5, 2, and 2 for the 9. Now that we are done solving the subproblems, we compare those candidate solutions and then we choose the one that uses the fewest coins. And that is 5 to 2. For solving the subproblems, we use the same procedure. The only difference is that we need to pay attention to two edge cases. The remaining condition reaching amount 0 and avoiding choices where we are paying too much, reaching negative amounts. To understand this better, let's take a look at the subproblems. And to be honest, we could do this process over and over again until we reach the bottom level, as you would say right here, which is 1, 0, or nothing right in there. Maybe it's a negative value. I don't care. I don't know that, but it's working like that. Driving the subproblems helps us see clearly the edge cases. When the amount becomes 0, we have to stop the iteration. Since the subproblem is solved and there's nothing left to be paid, we can see the 0 node in several of the subproblem trees. When the amount goes below 0, which is negative, then the given amount cannot be formed without coin. For example, trying to pay amount 3 using coin 5 would require solving the subproblem for amount negative 2, which does not make sense. So in addition to that, we can also notice that there are many redundancies. Maybe I read it wrong. I'm trying to read it again.
Redundancies.
Alright. So as you will notice that there are many redundancies among the subproblems. This is very important as it affects the performance of the algorithm. We originally thought about solving the problem using brute force, which results in a slow algorithm, where something like this, where the n is the number of coins and the y is the value of the amount we have to pay. In other words, the brute force solution has exponential complexity with very poor performance. However, now that we know that there are redundancies among the subproblems, we can catch the results to reduce the complexity to only O n way. In each step, we must try n coins, and we have up to way steps. In the worst case, we pay way with way coins of value 1. This result is great. We reduced the CAM complexity from exponential to polynomial. One thing good about the polynomial is that let me just draw a line. Okay, suppose this is how to say that again? I just forgot about that. Anyway, imagine this is a polynomial line, and you will notice when the y value, when its value get into a certain level, then no matter how you increase the x, the y value would always be still or keep a let's say stable horizontal line out there. So no matter how you increase the x, the y won't go up that much. So it's kind of stabilized. So in this case, no more term is required.
Coordinate.
Yeah, coordinate the plan. Now I know how to read that. Alright, we're now ready to write the first implementation of the recurrence without catching. This is because we want to focus on the logic of the recurrence without distractions. We will add the catching functionality later, but for now we'll just focus on the simplest version of the solution. Okay, let's get started. So at the beginning, we have to define a function. The function name for it is makeChange. And for this function, we would take the coins as an input and the amount also as an input. For the coins, it's a last. For the amount, it's an integer. Giving a list of coin values and an amount to be paid returns the shortest list of coins that add up to that amount. If the amount to be paid is 0, then an empty list is returned. If the amount cannot be paid using the coins, a known value is returned. And at the beginning, what we do at first is to handle those edge cases. For example, if the amount is 0, in other words, if the not within 0, if the amount is 0, if we add the not before that 0 numbers, we'll get this expression would be true. So in this case, we'll return empty list. And also if that amount is less than 0, which is negative, then which is a negative number, then we'll just return none. Yeah, those are the two edge cases. Then at the beginning, the optimal result is equal to none. We don't know the result yet, but we will find out. Consider all the possible ways to choose the last coins. How we would do that? Well, we just want to do an iteration. For coin in coins, we're gonna let's say for each coin, we're gonna call this function itself again. And for that case, the coins last would remain unchanged. That's the thing that we will keep fixed. But what changes is that the money that we left. For this case, that would be the amount minus the coin. For this case, we'll get the partial result. If the partial result is none, which is this one, that means that's not a right solution. And for that case, we'll just do a continue, which is we will skip it. But if it's not equal to none, which means it may success, it may be a good way or a good solution. It's probably right. So if that's the case, then we'll just add the partial result with a coin that we have used to the candidate as a candidate. You know what? For this function, for the make change function, since it will, let's say, call itself over and over again. So in the end, for the first time, if we got a normal value, if we got a value, let's say, if we get a last back, then that means that's a pass that was right. So if that's right, we got that candidate, and we're gonna do a check if the optimal result is none, which is we do not have a optimal result yet, or if the length of candidates less than the optimal result, because this one may, got changes with, sometimes or after this loop, so it may have some value. It may have a last with some elements inside of it, but what we need to make sure is that the length or the elements the candidates have less than the old optimal result. If that's true, we would say, the new optimal result would be just equal to the last that we have, or we just calculated out. And since we will try all those possibilities, so we're gonna let this loop run until the end. And after this for loop, we will get the definitely optimal result. And if we get that optimal result, we return it. Perfect. Yeah, I didn't know that. And to be honest, if you let me do this problem, I won't be able to find out the solution by myself in a very short time. So this algorithm implements the recurrence relation as explained above. Notice how we handle the edge cases at the beginning of the function before making any recursive calls to avoid infinite recursion and to keep the recursion logic as simple as possible. Yeah, that's true. If you got an infinite recursion out there, that means you probably did something wrong. And that shouldn't happen if you are writing some good code. This implementation has exponential time complexity since we have not implemented the catching yet. So let's do that now. Unfortunately, if we try to add catching, simply adding the IRU catch decorator, we will have a lasting surprise. This code will try to roll out an exception type error on hashable type last. Okay, this is caused by the ineligibility to catch the argument coins. Yeah, I know that because I once tried to do the same thing with a last or with a map, and it will also say that it's an unhashable type. So in the end, I probably just gave up that problem. But for this book, the author, he probably have a better way to solve it. So as a result, as a last, it is mutable, and the IRU catch decorator rejects it. The decorator supports catching only arguments with immutable types, such as numbers, strings, or tuples. This is for a very good reason, to prevent bugs in case mutable arguments are changed later. in case of less by using some function like append, deal, or changing its elements, which would require invalidating the catch. A joke circulating. Oh, sorry. What is that?
Circulating.
Okay. A joke circulating in software engineering circles says that there are only two hand problems in computer science: catch invalidation, naming sense, and off by one errors. Why I have read three cents out there. To address the former, the design of the IRU catch decorator takes the either way out. It avoids having to implement catch invalidation at all by only allowing immutable arguments. Still, we need to aid catching one way or another. We can work around the IRU catch limitations if we notice that we do not actually need to catch the coins last that is shared among all subproblems. We only need to pass the remaining amount to be paid. So we write a helper function that solves the subproblem, taking as arguments only the amounts. The coin nest is shared between invocations.
Invocations.
Invocations. I almost forgot the meaning of this, but it's just another word for the calling. For example, call function. One way to implement this is to make the helper function nested inside the makeChange function so that it has access to the coins arguments of the outer function. Yeah, this is let's say one thing good about Python. You could always define a function inside of another function. This is kind of magic, in other strong type programming language or compilable programming language, you probably couldn't have this feature. Yeah, that's so flexible available out there. Yeah, but anyway, this is what he did, and he does it pretty good. Another way is to transfer the makeChange function into a method of a class that stores the list of coins in a class member. The helper could then be written as another method of the class, ideally a private one. I think adding classes is overkill for what we have to do, so we'll not discuss that approach. Well, I think by defining a class is very common in, let's say, Java. For Java, it's probably a very common way for doing that. You define some common variables that would be shared among different functions that's bounded into that class. Here is a full solution that uses nested functions. makeChange, we get the coins, we get the amounts. Then we use the IRU catch with the max size equal to none, which is we will catch as many as possible values for this function. I mean the helper function. And then all those logic are the same. The only different part is that we're gonna return the function by using the helper function. It's kind of strange, but if you know Python very well, you could know what's going on there. At least I know what's going on there. I don't know you if you understand it or not. Anyway, I don't care. And then as let's say for this book, one thing good about it is that for each problem, he will try to give you two solutions. One is what he called up to bottom. This one, top down version. So what he did is that try to solve the last value or the last problem, then go down until the original elements, something like that. But here's another method which he called bottom up. For a human, for a general human, we probably couldn't just think away of this. It's too, let's say, difficult for us to do that. But I wouldn't meant to, read those code for you. Maybe you couldn't understand it, but let me just try it out. Once we have implemented the top-down solution, we can rewrite it as bottom-up. We start from the amount 0 and keep adding coins in all possible ways until reaching the amount to be paid. So again, we define a function called makeChange. To be honest, this will be makeChanges. Yeah, probably the change is a good one for this. Okay, so the change has another meaning, just similar to the coins. But I guess if he used the word of coins, it would be more obvious for us to understand what he was talking about. Yes. You know what? Whenever I see some code like this, it's pretty much, let's say, not understandable. I don't know, but maybe there are some genius could just write some code like this. But for me, I couldn't. Even for understand this code that could require a lot of energy on it. And to be honest, I don't have that energy for now because it's kind of late in the Chinese time zone. So I almost lost my all of my So I almost lost all of my energy on the night. So I couldn't read this. Normally I in the past I would like to work at night, for those foreigners, then sleep at the day. I feel like, it's a wonderful life. But for now, since I work in a company, I should work at the day while sleep at the night. And if I stay up too late, I would be, let's say, inefficient in the daily working. And that's probably not a good thing for my company, right? Since they have to pay me to do their work. Yeah, that's it. So whatever, as long as you could have a good sleep, let's say for 8 hours, it doesn't matter when you sleep, So let's say this is it. I think this is today what I wanna share with you guys, and I hope that this video doesn't bother you anyway. So that's it. I will see you guys in the next video. Bye.